I'm very pleased to introduce Sara Anna here, who's going to give the second talk about the deterministic lesson.
Thank you. Is this microphone working well?
Yes.
No? Perfect. Oh, that's... Well, let me first thank the organizers for inviting me. You might say, well, you're organizing this workshop yourself. So, well, in this case, I was only an advisor. So, another thing I would like to say is that these sheets I prepared some time ago, so I'm in that sense very well organized. But then I wanted to look at them again last night, and then my plug didn't work. So they're relatively new to me as well. So if you think what's wrong, then that's the problem. The story is about the deterministic lasso, so this sort of fits well within the talk that David gave just before me. The idea is here that well, you have the statistical problem of the lasso, and I want to separate the statistics, so the random part, from the deterministic part. And my point of view was a little bit like this: okay, if you can solve the stochastic part of the problem, then the deterministic part is for other people because I'm a statistician. But as I understand it now, it goes also the other way around. If you look at the noiseless deterministic problem, then statisticians can help to solve that with their point of views. Now let's see, here are some keywords. So what I would like to address is the high-dimensional problem, a regression problem, say, with many more variables than observations. So think of just linear regression, or maybe logistic regression, or any other type of regression, maybe density estimation, high-dimensional exponential families, and so on. So I'll consider some various loss functions and regression problems. And the idea to handle the high dimensionality is to use the lasso. This is a well-known idea. It's for the hard or the soft thresholding idea, and it's called lasso by Shirani. I'll address the problem of sparseness there, and a compatibility condition, which is something like the condition of Candice and Tao called the uniform uncertainty principle. I have to say a few words about that. Another keyword is an oracle inequality, which is saying that you behave as if you know which coefficients are relevant. And then the stochastic part is empirical processes. Now let's see. So this will be my setup. I have two probability measures on some space Z. Fix on space Z, P hat and P. And they're supposed to be close together to each other in some sense. The first one, P, is, well, as in statistics, the underlying probability measure is unknown. Or maybe if you are in numerical analysis, this is an intractable, or maybe in finance, often this is something which is intractable, maybe known but intractable. P hat is a known and perhaps random measure, random if it's based on observations, random observations. And then we use this kind of functional analysis type of notation. P of a function rho is just the integral dp, so it's the mean, and P hat of rho is the integral dp hat. So that's some kind of approximating, like I call it the average or the empirical mean in most of my talk, bearing in mind that you have estimated P by the empirical P hat. Okay, so I should say here now that this talk is really the theoretical kind of talk, so be prepared, so that's why I write integrals and things like that. It will be just theory. Here's a special case. If we have observations Z1 up to Zn, these are observations, say they are independent or weakly dependent and that sort of thing. Then we can look at the underlying, well, P will be the mean, the average mean, because they may not have identical distributions. And P hat is just the empirical average, often denoted by Pn. Okay, so Pn is puts mass 1 over n at your observations. That's something you can observe. So that's important. P hat is something you know, and P is something you do not know or you don't want to know. Okay, now let's consider the following parameter space, a space of functions. I call it boldface F with a norm, so it's a normed vector space, and loss functions which are indexed by these functions in this space F, and I assume them to be convex. So these are convex loss functions, and the overall minimizer is the target, the thing I want to estimate. I'll give you the examples in a moment. I call it F0, so this is important to remember. F0 is the target, minimizes the unknown quantity P of rho, and we want to find an estimator such that the excess risk is small, and the excess risk is the difference between the mean at F and the mean at the target F0. Okay, so that's the setup. Now I'll assume a margin condition, that's a kind of identifiability condition. I'll assume it here to be quadratic throughout the talk. It can be extended to other conditions as well. So suppose you are in a neighborhood of the target, say in L infinity norm, then the excess risk behaves quadratic. That's a condition. So you have to check that for your particular loss function. So let's see why should that be true. Now let's just look at examples. So suppose let me call this the observation space, are a vector of covariables x and a vector of response variables y, and y is say real valued, and x can be anything valued. The space of functions is the L to Q space, where Q is the distribution of x, say, and rho is some basis functions, and we define as a loss function rho of f of x, so the distance between f of x and y. So think of f of x as a predictor of y, and the loss is the distance between them in terms of the function rho, some function. So here are examples. This is the standard example, least squares. The logistic model, okay, so then y is binary, taking only the values plus 1 and 0. Density estimation, so suppose you want to estimate the log density, okay, then f is the minus the log density, say, and this is just the norming constant so that it integrates to 1. Boosting, then that's the exponential loss function, then y takes the values plus or minus 1. So boosting is in classification problems when you want to classify in, well, this is the binary case. Hinge loss, that corresponds to the loss function that you take for support vector machines, and so on. So the point is this rho function here is always convex, right? So it fits within the framework that I'm considering. And okay. So now this margin condition, that's this in these examples. So you have you want to minimize the difference between the predictor and y. So actually you can sort of take the minimum inside the integral. So you just take the expectation of the loss. So if you have observed y and x, so given this value of x, you just predict such that this loss is minimal. Okay, so you can do that for each a, and then you get the function, the target f0. So that is just minimizing, so to speak, over the whole space of all possible functions without assuming any restrictions. And then indeed, under some reasonable conditions, you have this margin condition. So this is just a loss which is now one-dimensional function of a. And if you have a two-term, so f0 minimizes this. So if you have a two-term Taylor expansions, the first derivative is 0, and the second derivative is hopefully not 0, but something positive. So that means that near this minimum it behaves quadratic. near this minimum, so not everywhere, but near the minimum. So then the excess risk, which is just, well, iterated expectations, it's the expectation of the conditional expectation. The excess risk is then indeed quadratic. Okay, so that's the standard case, quadratic excess risk. It's not true for Hinge laws, then it's not generally not quadratic. But that doesn't really alter the theory, but just to see the formulas more clearly, I restrict myself to quadratic excess risk here, or lower bounded by something quadratic. Okay. So to be sure, you can think of least squares in the rest of the talk, but it also applies to other problems. Then this is the loss function, y minus f squared. The target is just the conditional expectation. And the excess risk is just this L2 distance. Yeah? L2 distance with respect to the measure Q, the measure Q of the covariables, of the input variables. Okay. Now we do a linear approximation of this target. We take a linear subspace of the space of, well, this is a way too big space. We take a linear subspace. Oh, beta should be in RP. I don't want it to be one-dimensional. I want it to be p-dimensional. Sorry, there's a mistake here. This is RP. And p, so like here, a linear function having p coefficients, and psi, j are the basis functions. They depend on the particular application. P is supposed to be large here. So for the moment, I'm not having any number of observations in the calculations yet. But think of P as being large. So that's the problem we're facing, like in the talk of David. And what else? So and these basis functions, they could be your original observations or wavelets or interaction terms in some kind of analysis of variance problem and so on. So they are supposed to be given, and the betas are the parameters now to be estimated. So I'm not assuming here that the target itself, f0, is a linear function, but I'm just hoping that I can approximate it well by a linear function, and I hope that this approximation is also going to be sparse. But that's not something I can check generally, because I don't know the underlying target at all. So you just hope for it. So to estimate this target, I take here as an example the lasso, and it's defined as follows. You take this sort of empirical average plus the L1 norm of the coefficients times the smoothing parameter lambda, and then you minimize that over all beta. So beta 1 is the L1 norm of the coefficients. Yeah. So now we want to derive inequalities for the excess risk of this estimator. Okay. Now let's see. The best we can hope for is that to see what happens if we replace this p hat by the unknown probability measure p. So that's sort of the noiseless version of the problem, a problem without noise, and we want to be close to that. And to handle that, I think it's on the next slide. Let's see. Yeah. I first want to make this kind of relation between L1 norms and L0 norms, between sparseness and L1 penalties. And the way I do it is really simple. So I'll just to get, maybe it's something important at least for understanding the rest of the talk, I'll give you a little proof going from the L1 norm to the L0 norm. And the idea is as follows. So here's the sort of, think of this as the noiseless version of the problem where you replace p hat by the unknown p. And then solve exactly the same problem. And then you get an estimate, sorry, it's not an estimator. You get a solution beta 1, let's say. Let's call it beta 1. Now, suppose, well, let me call script j the number of non-zero coefficients of beta, and the cardinality j. So we sort of hope that this beta 1 has only a few non-zero coefficients, that it's sparse, that you can do with the sparse beta 1. So that this set is small cardinality. Now I'll compare this beta 1 with beta star. And beta star is the same kind of quantity. So here's the same. And then I replace this L1 penalty by an L0 penalty in the sense that it's based on the number of coefficients. So L1 norm is replaced by the L0 norm. Lambda is replaced by lambda squared. And there's some constant here, 2/3. Don't look too much at the constants. It's just that they are correct as far as I'm doing my calculations correctly. But they don't have real meaning, just that there is some constant, and I want to show them that you don't think it's something asymptotic. All the results I will present are non-asymptotic. And then there's a phi squared here. And phi squared is the minimum eigenvalue of the Gram matrix of the design, which I assume for the moment to be not 0, because I don't want to divide by 0, of course. So if this is just an L2Q norm, phi is just the minimal, phi squared is the minimal eigenvalue of the Gram matrix of the design. That's clear, huh? So this condition is, of course, maybe a little bit cumbersome if you think about it a little bit, because if you have your input variable and they are p-dimensional, then their covariance matrix is, of course, a p-dimensional covariance matrix. And if P is very large, this is a huge matrix. And in most applications, like with matchlets and so on, this matrix is overcomplete. That means that it's singular. So this minimal eigenvalue is going to be 0. So that's a very important point in the last few years, that you don't want to assume this. And I'll just relax this to a compatibility condition. It has to do with various norms, and they have to be compatible. So that's why I call it that way. But maybe that's not a good idea. Maybe we just call it something like a uniform uncertainty principle. So I'll come back to that later. But for just to understand the main ideas, let's just assume this eigenvalue to be positive. Then you have this following lemma. So this assumes the margin condition and that minimal eigenvalue to be non-zero. Then the excess risk of the L0 solution. Oh, sorry, the excess risk of the L1 solution, beta 1, is more or less similar to the risk of the L0 solution. It's bounded by a constant 3 times this quantity. So that's this should be a star again here. So let me go back to the previous slide. So beta star is the L0 solution. And I just take this where the minimum is, the value of the minimum, that's here, of the L0 solution, and this is the L1 solution, and they differ by no more than a factor of 3. So that's the main point here, actually, that the L1 and L0 are more or less equivalent. Going the other way is, of course, much more difficult, and of course you don't want the constants to be there, you want them to be exactly the same. But still, this from, for me it's okay with some constants. For the moment that's okay. So what I'll prove later on is that for the estimator, this is the noiseless version, but for the estimator, when there is noise, you have an inequality where the 3 is replaced by 12. So there's no real difference, but there are of course some bigger constants involved. So this quantity will play an important role. That's why I give it a separate name, epsilon star. Epsilon star, you can think of that as the benchmark, the oracle rate, the kind of rate of convergence or the kind of inequality we want for the excess risk of our estimator. Because if we would know the true underlying measure, we cannot do probably much better than that up to this equivalence between L1 and L0 norms. So maybe it's nice to give a proof, because I think I have enough time for that, and it's a workshop, so we should work. Because what I'm presenting here are all very, well, the calculations are very straightforward, actually. So there's nothing deep going on here. So let me try, maybe I can have some light here. Let me try to prove it. I don't know if I can do it. Let me copy this first line. Oh, there's already something missing. Please erase. So this should be obvious because beta 1 is the L1 solution. It minimizes this type of quantity, so it's less than the same quantity at any other beta. Okay? Okay. So let me rewrite it in this way. So what's this? So beta in is inside the set. So I'm hoping that this solution has only a few non-zero coefficients. And those coefficients I call the set in, and everything outside that I call out. So beta in is just the set of coefficients where this kind of oracle beta star has non-zero coefficients, and beta out is the rest. Okay. So here I just can write this L1 norm here as beta in plus beta out. And here the beta in plus beta out, but beta out is 0 because that's by definition. There the coefficients are 0. So let's see. Well, I can forget about this, I think. I hope. So let's see, then we get no, this goes up, no. So you just bring this to the other side, this one. And then I use the kind of triangular inequality, you get this. Yeah, and that's the main trick. So now you apply so I replace this L1 norm by the L2 norm. And the number of coefficients here is j. That's the dimension of this vector. So I get a square root j in front. I think I called that j beta. And the L2 norm. And then you get a 2 here, sorry. Okay, now I'll go to the next, go back to the sheets because the blackboard is full. So, so we're now here. So this quantity, I just replace the L1 by the L2 norm. And then forget about the in, that makes it only larger. And then use this minimal eigenvalue condition to replace it by the norm of the functions. And then you get the phi here. And then use the triangular inequality. So you get f beta 1 minus f beta star. I insert this target inside. That's triangular inequality. And then put it back in here. Huh? We go back there and we have an inequality. But before doing that, I use a times b less than a squared over 2 plus b squared over 2. So go back to my quantity here. So this is my a times b. And then I get an a squared over 2 times plus b squared over 2, and I do the same, an a and an b. You get a squared over 2 and b squared over 2. So what I end up with is twice this quantity, so that's a squared plus b squared over 2 and b squared over 2. They are here, sorry. And then I insert that everything in here, so you get it here. Huh? Okay, so what you end up with is the excess risk of the L0 solution times 3 over 2. And this term I can put on the other side. You get 1/2 here. Okay, and that's it. That's the proof. That's all. So the proof itself, you see that there's nothing deep going on. You have this result, but it's sort of, in my view, at least the basis of what is to follow. Okay. So, yeah. So now I have to go to the error, because now I want to show that something similar holds for the original problem where you don't know this underlying p and you have to estimate it. So then you have to look at what should I do with the error, and it turns out you can deal only with this quantity. So you look at the difference between p hat and p, evaluate it at the loss functions. At the distance L1 distance beta minus the L0 solution less than some constant m. So that depends on m. Uniformly, so look how large can that quantity be. Okay, so think of this, so that's in general, if p hat is the empirical measure, this is a random variable. So this is a random quantity, so that's why I put the hat on it. But you can usually find a bound such that this is less than epsilon star for a fixed value of m up to a certain set which has small probability. And this is this m star. So m star is something like, well, something close to this maximum, but you think of this m star as being non-random to make things look in the standard way they should look. So I look for a non-random m star such that z m star is less than epsilon star, and epsilon star is written in this form, and lambda star is called epsilon star divided by n. You think of that as something like a smoothing parameter, so it's the same idea, lambda and lambda smoothing parameter, and this lambda star are about the same order later on. So here's an example. Oh, I'll see if there's time, we'll see that. In typical cases, the empirical process behaves like lambda star times the radius of the balls you're considering, where lambda star is of this order. So log times log the number of variables divided by the number of observations if you have IID observations or independent observations, and the square root of that. Okay, so that's true for any m, or maybe any m small enough, so it will be true. I only need it to be true for one fixed m, but generally it's true for any m, pointwise in m, not uniformly in m, but pointwise. Okay, now I come back to this eigenvalue condition. Remember that was a bit of a nuisance, and to my knowledge the best we are at this point, maybe Peter can help me, is the following. So it's something like, Peter called it, I think, the the generalized eigenvalue condition or something? Sasha called it, yeah. Okay. So the idea is a little bit, you only need something like a little bit more than identifiability of the oracle or maybe the minimum L0 solution, and not identifiability all over the place. So you don't need all the eigenvalues to be strictly positive. Well, now the condition goes like this. For a subset of the indices, so say a subset of the coefficients, think of that way, and a constant phi. Phi is again something like an eigenvalue, but now a generalized eigenvalue depending on this subset. It's true that as soon as the L0 norm of the out coefficients, well, out depends on the set you're considering, is less than 3, sorry, the L1 norm, less than 3 times the L1 norm of the coefficients inside the set, if only for those coefficients, we should have something like, well, this kind of behavior, and then the the minimal eigenvalue in there. So, okay. So it should not be true for any beta, but only for a subset of the beta satisfying a very strong condition. So if I have time, I can go into details when this is true, but we'll see. We'll see about that. So I'm assuming from now on that this is going to be true. Okay. Okay, now so for each beta you have something like an eigenvalue associated with it, because it's a generalized eigenvalue condition or compatibility. Call that phi of beta. And then beta star is like before, exactly the same quantity, except that now I don't assume these eigenvalues anymore, I assume these generalized eigenvalues here. So that means that this quantity may be different. So this, well, maybe, well, you're sort of trading off not only the excess risk, but also the behavior of the eigenvalues and the L0 norm of the coefficients. Okay, and then let me call where the value of the minimum of this quantity epsilon star times 3. That's the coefficient. Okay. Then you can prove the following theorem, again with this kind of arguments. If your smoothing parameter in the original problem is bigger than 8 times lambda star, and lambda star is the quantity relating the p hat, the estimator, so the difference between p hat and the underlying measure p. That's this parameter. Okay, if you take it big enough, then the estimator has excess risk plus L1 norms, no more than 4 times epsilon star, and epsilon star was this L0 solution, which was I've written again here. 3 times the L0 solution, so you get a 12 here. Okay, and then I have to write down, of course, you need this margin condition. I gave it in the beginning. The margin condition is quadratic behavior, which is only in a neighborhood of the target. So I need to assume that my estimator is eventually, or in some sense, if I do the right calculations, in the neighborhood of the target. And that is okay if I assume this. So if I assume that I'm in this L1 ball, something you can never check in practice because it all depends on the sparsity, but just hope for it. If I'm in this ball, that then my functions are bounded. So that my functions are in this neighborhood where the margin condition can be applied. Right. So if you think of this condition vanishes as soon as you have quadratic risk, because there the margin condition is always satisfied, even outside, it's very far away from the target, it's always quadratic, so then there's no condition here. But for logistic regression, you have to really first, you need this. Okay. So just a few words on that, it's not so bad. So remember that my functions are linear functions. So if if I'm in this L1 neighborhood, then the L1 norm, the L infinity norm is bounded by m star times k, where k is a bound on the base functions. So if they are bounded or not too large, this may be very large, then I assume, well, actually, if my asymptotically speaking, if the L1 norm goes to 0, if I can prove that, this m star goes to 0, then this will be hopefully bounded. Something, again, you just have to do the calculations for particular cases. So this is asymptotics, the kind of asymptotics you can get out of it. So far it was non-asymptotic. But in typical cases, the smoothing parameter can be taken of order square root log number of variables divided by number of observations. Now assume that at the oracle the generalized eigenvalue is bounded away from 0. And then this is the oracle rate, so to speak. And then what we've shown, if those two terms are of the same order, you trade them off. So suppose they're of the same order. So they're of the order, say, of the second term, which is then of order lambda squared times the number of coefficients, which divided by something which is supposed to be staying away from 0. So then you get this order. And lambda squared is this term of this order times the number of coefficients. Okay, so asymptotically speaking, you get some rate which corresponds to knowing the number of knowing which coefficients are non-zero. That's this one, j over n, and the log number of variables is the price to pay for not knowing that beforehand. Okay. And if you go on with the asymptotics, so if the base functions, the original raw data, say, if they are bounded, and then we get, well, this is my m star, I didn't write it down. M star is epsilon star over lambda star, maybe you remember that, times k. That should be then bounded. Well, in this case, it's of this order. So you get that your estimator has a bounded subnorm if the number of coefficients of the oracle is of smaller order square root of the number of observations. And that's sort of kind of familiar type of conditions that you see in this kind of work. So now I just have to say a few words about so particular case when you have independent random variables. So the point is actually that the whole theorem, you separate stochastic part from deterministic part. And so this is about the stochastic part, going back again to that. And it's relatively easy to handle in the case of independent observations because we have concentration inequalities and that sort of things. So suppose that p hat is the empirical measure of n independent observations. And let's assume that the base functions all have theoretical norm equal to 1. That's of course not something you can assume without loss of generality, because in practice what you do is you renormalize your base functions with the empirical norm instead of the theoretical one, because you don't know it. But the theory is easily adjusted to that. It's not an additional theoretical complication. So don't worry too much about this. But once they're normalized, assume that they're also bounded by some constant k. That I call condition k for this constant k. And condition L is saying that if I'm in a neighborhood of the target, my loss function is Lipschitz. So that's true for all the examples I showed, for any neighborhood, except for the least squares case. They are not Lipschitz, but only, of course, in a neighborhood. So that's why, in a sense, least squares is more difficult than other loss functions, but still. So if you assume those two conditions, then the expected value of the empirical process is bounded by lambda star times the radius m. And lambda star is, well, some quantity depending on this Lipschitz constant and on the constant bounding the base functions. But the main term in general is square root log 2p over n. This is generally, well, depends on p and n, of course, it's not asymptotic. But it's most typically, we think of this as smaller order if k is bounded and p is not exponential in the number of observations. Okay, and then there's a little bit technical conditions here, which I don't want to discuss, but just so that it's all there. Right, so then we have the mean value of the empirical process, and then we can go on with, well, the concentration inequality says that it's close to its mean value, so there's no additional complication there. For instance, you can use Bousquet concentration inequality. So if functions are bounded and have some variance, and if you look at the sub of the empirical process for independent observations, then the probability that the empirical process is further away from its mean than this quantity is exponentially small. Okay, so this is the conclusion of that work of probability theory is that you can take your smoothing parameter of this order. Okay, and then you have to work out the constants, but of course the constants, they are in principle all there, but they will not be of any practical value, I guess, so that's okay. So what I should say here again is that with this lemma, to prove this is very easy. Oh no, in general, you need some kind of contraction inequality there to prove that. Okay, but that's all separate from the main theorem. Let's see. Let me just go back to that. Let's see. So this theorem doesn't use any statistical arguments, so it's really separate from that. So in a way, the statistics and numerics are different. Okay. So a few words about this compatibility condition. This is this generalized eigenvalue condition. So if your parameter space of functions is just the some L2Q space, say, then we write sigma as the variance-covariance matrix of this space. So then the L2 norm is just this quadratic form, okay? Now, bear in mind that we only want eigenvalues to be small in certain subsets, or large in certain subsets. So let's partition this matrix. Say this is the set, maybe of the oracle of non-zero coefficients, and what's happening here, here, and here, I should not be too worried about. So in principle, what you would like is that for the oracle, this set has a non-zero eigenvalue, and then the rest, well. So let's, now, the idea is, in the paper of, I think Candace and Tao were the first to think of this, to not take just here the oracle set, but to extend it a little bit. Say twice as big, make it twice as big. Or 3 times, or something of that form. And then there are also papers by Sasha Tsibikov and co-authors, Wegkamp and Unea, and they use different kind of conditions. So I think in general it's something of this form. You look at the minimal eigenvalue of the, say, the smaller set, and then you have to do something about the correlations with the coefficients that you don't, which are not relevant. And that's expressed in an expression of this form. Okay, so I think Candace and Tao take Q here equal to 2, and if you look at different papers, they take different versions of Q. It's an LQ norm, so it could be Q equal to infinity or Q equal to 1, and then you get all various conditions. And these compatibility conditions or generalized eigenvalue conditions can be shown to hold if this ratio is sufficiently small. And then in a lot of parameters you can choose your LQ norm, and you can choose, so you have to extend the set a little bit, maybe make it twice as large, or 3 times, or take the whole set. There also you can make various choices. So I don't think at this moment the story is completely finished. I think there's still research to be done, but for the moment it's really important, because this compatibility condition for the moment is still not very satisfactory, I would say. Okay. So here are some references. This is the concentration inequality I presented, and this is where this, well, this is I think the more important paper for finding, well, it's a different type of problem considered there, but you can see that the lasso and the Danzig selector are very similar in a certain way. And here are some papers that I'm using mostly. So if you want to learn more about what I talked about, it's in those 2 papers here. Okay, well, I think that's it. Thank you very much.
Sarah?
Sarah, both you and David in the previous talk emphasized the importance of sparsity in being able to resolve the large P, small n problem. Clearly, when you are able to find when it is sparse and you are able to find a sparse solution, then you know that you're probably okay. If it's not sparse, is it likely that you will fool yourself into thinking that you have found a sparse solution?
Well, I don't know. My feeling is that you will not fool yourself, that you will find as many solutions as you have observations. But
So we have some reassurance
that
then
I don't know exactly. I mean, these results, they don't really assume sparseness, but if it's not sparse, then they don't tell you anything. Let's see. So if it's not sparse, this term is going to be large, right? So that's just not going to tend to 0, the second term. And the first term neither, I mean.
I was
I don't know.
wondering in case if you can estimate proportion of non-zero predictors. So in that case, if your estimator is consistent, maybe you can say something about it's sparse or not.
Yeah, so it's consistent on the fairly general conditions, but still I think the number of relevant coefficients should be of smaller order than the number of observations, as far as I know. Otherwise it will not be consistent even.
You can divide the signals into two classes, very small signals, large signals. So
Yeah.
I think in quite general case, maybe you can give a consistent estimation of the proportion of the relatively large signals.
Mm-hmm.
So in that case, you can at least say something about sparsity with just some random source.
Yeah, because if it is sparse, there's no hope that you can tell how sparse it is in this sense. So.
You want to ask your question?
So once, so when you have a high dimensionality, you could be interested in two things. Either estimating the beta part or the x beta, which is what you're doing here.
Yeah, and the beta part as well, because it's there, the L1 norm of the beta part.
Sure, but let's look at the x beta part, the f beta. So when you want to estimate the beta part, even if I tell you which variables are important, you still need to be able to go from data space, from y to back to beta. And so a subset of x needs to be invertible. And so these conditions about, submatrices being invertible and maybe even well conditioned if you want to avoid blow up when you have noise are very sound, and it's very difficult to do without it.
Yeah.
But once you only care about x beta, they become far less important, right? Because if you could have even like two columns that are exactly the same, but when you want to predict for x beta, whether you use one or the other, it doesn't really matter. So what's your take on this? Which is why do we have to have conditions about once you're only interested in the prediction error, not on going back to beta, but just
I just don't know, but my feeling is that it's the problem that they should be here with the lasso, but it's obvious that you can do without them using other methods. So it's something like a drawback of the lasso, I would say. That's my feeling, but I don't know if I would ever be able to prove that the lasso needs some condition. That I don't know.
Actually, I guess Prof and Vital and I sort of kept on throwing that question around, and we were never able to get rid of that. And I guess it somehow is that although the prediction part of it is invariant, the lasso isn't.
That's correct, but you don't need. Okay, so maybe we'll discuss this on Wednesday, because we have new results where you basically have no assumption on
At
x.
all?
Almost nothing. and then if you care about x beta, then
Okay, well that's good. I mean, the other thing I just wanted to mention was that in some sense, your title, the deterministic lasso, somehow suggests that it's well. I somehow would it be fair to say that what you that what you're doing is you're looking at the bias, right? I mean, the
Well,
first calculation is a bias calculation.
Yeah, no, not really, because the deterministic is more or less that I'm just looking at two probability measures which are in a certain sense close, random or not. As soon as they're random, I'm looking at the set where they are close, and the whole random thing is not playing any role. There's
Well,
no.
except that there's a probability measure.
Well, there's an
You're
integral.
looking at the population. You're looking at the population version in some sense. Is that fair?
No, I'm not only looking at the population version, of course. So there's a population version on the right, and on the left is the empirical version, or whatever. I mean, it's, yeah.
But for your first part, wouldn't it be fair to say that
This is
that was
the population
Yeah,
version.
exactly.
Yes. Yeah.
Well, we're now going to break for lunch till 2 o'clock. For the people who are presenting posters, just to remind them that they have the opportunity towards the end of the afternoon to whet our appetites by spending 3 minutes to help with one transparency, giving us the bottom line of their posters if they wish. I guess it's not obligatory, but if they want to have that opportunity, then it's going to be there. So we'll now close the morning session with thanks again to Sara.